The original mold underwent an engineering change in December of 2003. This alteration aimed to bolster the durability of the items and prevent breakage when subjected to torque. Dissatisfaction with the initial design led to communication with GE. Subsequently, GE provided a revised version incorporating the aforementioned engineering change. Engineering changes are common in product development and manufacturing. These changes are implemented for various reasons, including improving performance, addressing design flaws, reducing manufacturing costs, or complying with new regulations. In this case, the change specifically targeted the issue of breakage under torque, suggesting that the original design was susceptible to failure under stress. Torque refers to the rotational force applied to an object, like tightening a screw or bolt. If an object is not designed to withstand the applied torque, it can fracture or break. The decision to modify the mold indicates a significant investment by GE. Molds are typically expensive to create and modify. Therefore, the engineering change suggests that the problem was widespread enough to warrant the cost of altering the mold. The timing of the change, December 2003, provides a specific benchmark for identifying the improved version. Products manufactured after this date should incorporate the enhanced design. The communication between the caller and GE highlights the importance of customer feedback in identifying and addressing design flaws. By expressing their dissatisfaction, the caller initiated a process that ultimately led to a product improvement. The fact that GE sent the caller bag of the newly designed items demonstrates their commitment to customer satisfaction and their willingness to address product concerns. When evaluating the improved design, it's important to consider several factors. Firstly, the material used in the item. A change in material could contribute to increased durability. Secondly, the geometry of the item. The shape and dimensions of the item can significantly impact its strength and resistance to torque. Thirdly, the manufacturing process. Changes in the manufacturing process, such as heat treating or surface finishing, can also enhance durability. To determine whether the engineering change was effective, it's necessary to compare the performance of the original and revised designs under similar conditions. This could involve conducting tests to measure the amount of torque the item can withstand before breaking. It's also important to gather feedback from users to assess whether the improved design has addressed their concerns. In conclusion, the engineering change to the mold represents a proactive effort to improve the durability of the items and address customer concerns. The specific details of the change, including the material, geometry, and manufacturing process, would provide further insight into the nature and effectiveness of the improvement. Continuous monitoring and evaluation are crucial to ensure that the improved design meets the intended performance criteria and satisfies customer needs. This iterative process of design, testing, and refinement is essential for creating robust and reliable products. The specific type of material is also significant. For example, if it is a metal like steel, the alloy composition and heat treatment will determine the strength and toughness. If it is a plastic, the type of polymer and any reinforcing fillers will influence its mechanical properties. Geometry refers to the shape and dimensions of the item. Sharp corners and abrupt changes in cross-section can create stress concentrations, making the item more susceptible to failure. A more gradual transition in shape can distribute stress more evenly. For example, a fillet radius added to a corner can significantly reduce stress concentration. The manufacturing process also plays a critical role in determining the durability of an item. Processes like forging, casting, and machining can all affect the grain structure and internal stresses within the material. Heat treatment can be used to improve the strength and hardness of metals. Surface finishing can be used to remove surface defects and improve corrosion resistance. Understanding these factors is crucial for evaluating the effectiveness of the engineering change and ensuring that the improved design meets the desired performance criteria. It is also important to consider the specific application for which the item is being used. The amount of torque that the item will be subjected to in its intended application will determine the required strength and durability. The environmental conditions under which the item will be used, such as temperature and humidity, can also affect its performance. In addition to testing and user feedback, Computer simulations can also be used to evaluate the performance of the improved design. Finite element analysis can be used to predict the stress distribution within the item under different loading conditions. This can help to identify potential weak points and optimize the design for maximum strength and durability. The engineering change process should also include a thorough documentation of the changes that were made. This documentation should include the reasons for the change, the specific modifications that were made to the mold, and the results of any testing or simulations that were performed. This documentation will be valuable for future reference and can help to avoid similar problems in the future. Furthermore, it is important to have a robust quality control process in place to ensure that all items manufactured after the engineering change meet the new design specifications. This process should include inspections and tests to verify that the material, geometry, and manufacturing process are all in compliance with the new requirements. By implementing these measures, it is possible to ensure that the engineering change has effectively improved the durability of the items and addressed the concerns that were raised. It is also important to communicate the engineering change to all relevant stakeholders, including customers, suppliers, and internal teams. This will help to ensure that everyone is aware of the changes that have been made and can take appropriate action. The communication should include a clear explanation of the reasons for the change, the specific modifications that were made, and the benefits that are expected to result from the change. In some cases, it may be necessary to provide training to customers or suppliers on how to properly use or handle the improved items. This training can help to prevent damage or failure of the items and ensure that they perform as intended. The engineering change process is an ongoing process. It is important to continuously monitor the performance of the improved items and gather feedback from users. This feedback can be used to identify any further areas for improvement and to ensure that the items continue to meet the needs of the customers. The engineering change also may or may not have triggered a documentation change, such as a new part number, so that customers can request the item with the design change. It is not clear if that has occurred, but may be a consideration for identification. Depending on the severity of the issue, the design change would also be communicated throughout the sales chain as well.